university where he is right now. So his research focuses on processing structures and mechanical properties of metallic alloys, composites, and foams. And Professor Dunand has a lot of awards. He's a fellow of the ASM International, a fellow of the TMS, the Mineral, Metals, and Materials Society. Is as well the 2012 Material Science and Engineering A Journal Prize awardee. Is a distinguished scientist. He also got the Distinguished Scientist Engineering Award from the Structural Materials Division of the TMS, and he's been 3 times Departmental Teacher of the Year at Northwestern. Dunand is also a co-founder of Nano.
So you can do this. Yeah, we should. This, can we get rid of it as well?
Yeah, just more.
Yeah.
And
Like floating meeting control.
Might be a bit.
This one.
yeah.
There we are. We're in business. All right. So it's a pleasure to be here in the mechanical engineering department, and I thought I would talk about some manufacturing aspects where there's an overlap, I think, really between material science, which is what I do, and mechanical engineering. And in particular, there was interest, I'm going to talk to the host here, to talk about not so much the additive manufacturing, laser, melting of metals, but rather this ink printing that is kind of marrying the properties of a polymer type of additive manufacturing, but eventually fabricating metallic structures via ceramic precursors. So I'd like to acknowledge, of course, the many students, postdocs who have been involved in this work, as well as colleagues, including Ramil Shah and Ralph Spolenak at ETH Zurich, who was also involved in the tungsten part that I will describe at the end of the talk. Working? Because it's hidden.
We just have to click back on the presentation. Because if you clicked on the Zoom, sometimes the Zoom window's up.
So go back here. Yep, you fixed it. Thank you. So I will be talking about specifically micro-lattices, often called scaffolds. And I don't think I need to introduce why we're going to do this. It's really to get high strength, high stiffness, low density, lightweight materials really that are metallic. But I want to talk about the many ways that people have done as an introduction have made those materials. We can cast, essentially lost wax casting. This tends to be rather large, is 1 inch roughly, or you can make electroplating, which is extremely lightweight and much finer. You can use wires that can be assembled, bonded, brazed, etc., into those, or even woven into those 3D structures. And of course, from liquid to wires to powders, we can use additive manufacturing using powders, where typically people melt with laser or E-beam, and also in some cases sinter the particles, which is, of course, a slower process, but is not quite as extreme in terms of temperature cycling of the material. So this is the way it's done. And of course, I think we're all familiar with the high temperature energy-based additive manufacturing for metals, where typically melting or even sintering with laser or E-beam, and you create those beautiful structures. They can be bulk, or they can be, in some cases, also micro-lattices. So that's the metal world. And then the polymer world, of course, is that at room temperature, you extrude a polymer structure. But of course, those are polymers, so they are really good near room temperature, not for extreme temperatures. And the idea here is to kind of adapt to metals what is currently done for polymers, and that is this ink printing that I and many others in the field have been exploring as a way to get the advantages of low temperature in printing, and then only after the structure has been made, transform it to metallic structures. So for the case of metal powders, so if we load that ink with metal powders, you can extrude that suspension, if you want, of metal powders and fluid into a 3D printed structure. You can burn out the polymer, sinter the metal, and you end up with a metallic structure. The unavoidable issue is shrinkage. So there's going to be shrinkage like anything that is sintered, but you also have to worry about warping, cracking, and or incomplete sintering, in particular if the shrinkage is anisotropic. So that's one thing that we were worried about when we started. What we are proposing is to actually do a bit of a roundabout. Instead of printing a metal powder that is in a paste here, we're actually going to print an oxide powder. So a good example would be iron oxide. And the reason we do this is that we can reduce the oxide with hydrogen and form iron, and then burn out the polymer and sinter the metal. You say, well, why go through that? The main reason is that we can use submicron oxide particles, whereas for metal powders, it needs to be quite a bit larger. And using submicron powders allows us to reduce and then have extremely fine nascent metallic powders that will then sinter much, much faster. So that's why we go, even though I will describe both cases here. So this is an example of that ink printing of a highly loaded oxide powder material. And we can see the overall micro-lattice structure. This is room temperature for the synthesis and the printing. Very simple sintering. So this is very standard vacuum, argon, or even hydrogen for the reduction. Low powder beds, of course, which allows us to have closed volumes. We don't trap powders. We can grade composition with multiple nozzle, wide alloy combination if you are using blends of elemental powders or even pre-alloyed powders. Really no drying or curing time. This dries near instantaneously via fast evaporation, and really high loadings of particles, which is going to be important for the sintering step, because we want this to sinter. And Professor Shah, my colleague, also is not just doing metals, but she's also doing polymers, biological materials, ceramics, and others. But we have now to deal with the removal of the polymer and the subsequent sintering of the powders, which leads to shrinkage, which is okay and unavoidable, and hopefully no warping or cracking. Because after all, one of the reasons we do this is to avoid the cracking that happens in other melting-based additive manufacturing, where the thermal gradients are really often cracking the material. So here's in principle how it works. We are creating a suspension with the metal particles or the oxide particles. We have a binder, which is a polymer, and the solvent. The solvent is dichloromethane that evaporates very quickly. As I said, we add surfactant and plasticizer if we want to have really flexible structures that we can bend and do origami, as I'll show you in a second. We then thicken this ink to the point where it's typically kind of almost the viscosity of honey, and can still be extruded through a nozzle where you now 3D print at room temperature in air those loaded inks, and then you further evaporate the solvent. So now you precipitate the binder that becomes a polymer matrix that contains the particle, and you paralyze, so you burn out the binder. That's where the first level of shrinkage happens. And then if we have an oxide, we reduce it with hydrogen and then sinter it to metal. So that's in principle the path for the manufacturing path of those structures. So this is of course accelerated here, but you see, for instance, a iron oxide inks that is essentially rust, high purity rust, and you can really create, in that case, a demo piece, a little octopus out of the oxide, which will then be reduced to pure iron. So if you look at the particles, they are clearly submicron. They're also clearly closely packed, after the extrusion. So after drying, you have this porous solid that is strong enough with a little bit of binder can be handled without fracture, and so we can go and do the sintering. And this is the kind of viscosity that we have in base. So it's very inexpensive if you think of it. You need a room temperature polymer 3D printer and a sintered furnace to achieve those. So here's an example of a thin sheet, 5 layers only. We can use it quite big, as you can see, and we can use those thin sheets to create 3D structures by cutting and bending, so origami and kirigami in principle. I'll show examples. Or you can make extremely long, this is again, of course, accelerated, but extremely long structures. This is 14 centimeters high, and you can see the detail of that inner webbing of the structure, creating strong, stiff, and oxide, in that case, iron oxide, that will then be reduced to metallic iron. So a few examples of various oxides. So we have nickel oxide going to nickel, copper oxide that will go to copper, and of course, you can start mixing oxides. So iron and nickel oxide obviously will go to iron nickel, which is kind of a prototypical steel, which will allow, and here the additional issue is the interdiffusion. Once you reduce the oxide, you have pure iron, pure nickel. So not only do you want to sinter, you also want to interdiffuse to achieve a homogeneous alloy. So that gives us an extra lever. So in principle, it's pretty much any metallic composition for which the oxide can be reduced with hydrogen, which gives us at least a good 8 practical elements. Cannot do it with titanium, but we can do it with iron, nickel, cobalt, copper, tungsten, and even molybdenum, as I will show in a minute. So the inks can be printed pretty much always under the same conditions. It's only a question of how big the particles are, but the sintering and reduction now depends on the temperature at which the reduction takes place. So here we may have different times and temperature. This is temperature, this is time. You see an example for cobalt. There's reduced relatively short time at 900 degrees C. And here's an example for nickel that is reduced at a much higher temperature, because we have to both reduce and sinter the material. So that now becomes a bit of an optimization process to find those temperatures and times. So those relatively heat treatments, simple heat treatments. The really important thing is this is a slow cooling. You can do just in the furnace. And so there's really very little internal stresses and, of course, no cracking in the materials. Even if you are actually working on relatively brittle alloys that would crack very, very easily under selectiveness and melting conditions. And so here are examples. You see the dramatic shrinkage as you go from iron oxide to iron, or this mixed kind of, well, this is actually an Invar type of alloy. And you go from oxide, red, to the metallic shiny material. But what's really remarkable, at least for us, when we did this, is that there's absolutely no distortion in the material. It shrinks in an extremely uniform manner. And the trick here is that, as you can see, we don't have, this is not a bulk material. This is a hollow structure. And each of those little struts is shrinking at the same rate. So the whole body shrinks. But so you say, well, that's not very useful because your dimensions are changing. Yes, but it's reproducible. And that's something that happens routinely in the powder metallurgy industry, where the shrinkage may not be only 10 or 15%, but as long as you're reproducible, you can oversize and then end up with objects that are close to net shape. And you may need to be a bit modeling, a bit of machining to achieve your final shape. Maybe not on a complex shape like this, but maybe on structures like this. Now, let's look at, a little bit at the quality of the printing that is achieved after this reduction in sintering. So this is SEM. You see extremely smooth struts, as we call them, in this lattice. And if you go to even higher and higher magnification, you see how extremely smooth and notch-free the material is. That's because we are using sub-micron particles, tiny, even to that 20 micron, that all sinter and create those smooth surfaces. You may see a few grooves here due to grain boundaries. This is, if you try to do this with a laser, like the laser track might be actually almost that thickness, you get extremely rough surfaces and therefore problems with fatigue resistance. So this sintering of sub-micron in situ created metal particles from oxide allows us to achieve very, very good surface quality. So a quick few examples. We've seen the lattices. You can do structures that have open spaces. Here's a box, a fully enclosed box. We cut it. And so you see here, for instance, that the ink is sufficiently viscous that it doesn't sag as you're going from one end to the other. So we can really close structure, impossible with a powder bed, for which the powder would be entrapped in the closed cavity. And I promised already the origami, so this is the unavoidable crane that we can make from sheets that are then, in that case, done by hand. But that's really feasible if your polymer, you can choose it, is flexible and flexible enough for that kind of work. And you can actually also print two pieces separately and then merge them using a little bit of solvent, and then do the full sintering on multiple pieces that have been welded or glued, if you want, with a bit of solvent. So it's very nicely flexible in terms of many design structure that we can make. Now, the mass, not only the volume is being reduced, not only shrinkage, but of course the mass is being reduced as well for two reasons. One is we are burning out the polymer, so that's gone, and then we're also going from the oxide to the metal. And so what kind of mass reduction do we have? Well, we see that for iron, nickel, copper, and then those alloys, it's anywhere between 30 and 40%, depending on how much polymer we have, and of course, the unavoidable reduction from oxide to metal. Meanwhile, we see that the volume reduction is quite drastic. You saw it, with your own eyes with this incredible shrinking that we get. So as high as 80%, and in other cases, a bit less. And when it's less, it's because we have some residual porosity. So really the sum of the shrinkage plus the residual porosity gives you the total shrinkage. So here's iron, very large shrinkage or zero residual porosity. So the struts are dense now. Or at the other extreme, here is, for instance, nickel, which already still has about 30% residual porosity. So that's interesting. It means that depending on the level of sintering, we can maintain some extra porosity within the struts, which would further make it lighter. Or vice versa, if we want something strong, we may want to sinter completely the material and not have residual porosity. So here has a good example about the iron that, as you zoom in, this is a cross-section, this is the SEM with solid. And then the cross-section here shows barely any porosity. This is a 25 micron bar. On the other hand, nickel, which is now highly porous, you can see pores in the surface. It's actually open, right? So this would be a very nice structure if you're interested in catalysis and in a very high surface area, while still maintaining an architecture for the catalyst. And the difference between the two is really the packing of the particles as you print. If they're sufficiently close to each other, then everything sinters together. But if there's a lot of extra material, in particular, if you have some binder that is burned out, you may end up with those meandering, open porosity structure. So you also have now another ability to change the internal porosity of the struts beyond, of course, the printed channels. That is the macro porosity in the material. Other examples for copper, cobalt here, an extreme case of on-purpose under sinters. We get extremely high porosity. It's still strong and continuous in 3D, but you get really, really high surface area as a result. So far I showed you the case where we use oxide particles. Now we can also do it with metallic particles, albeit those are going to be larger particles because they're metallic and otherwise they will catch on fire if we're using super fine. So here's metallic nickel particles, which may be 10 micron in diameter or so. And we see that we end up with perfectly fine and nice metallic structures. We have to be a bit more careful now about the binder during decomposition, not contaminating the metal. The other advantage of using an oxide is when we burn out the binder, there's no contamination opportunity. Whereas if you burn out the binder in the presence of metallic iron, you may actually collect some of the carbon and end up with an iron-carbon alloy, aka steel, rather than pure iron. And copper, of course, doesn't have this issue because there's no solubility, no chloride. Meanwhile, you see that the shrinkage, right, for pure iron powders is only 15% as compared to what we had for the printed oxide, which was 40%. It's a combination of not having to lose the oxygen and also of a better packing of the particles as printed. So there's also variations here between the metallic route versus the oxide, a bit more complex route that I discussed. So, and if we look a little bit more detail, here's the iron powders. Here they're about maybe 2.5 microns in diameter. There are nickel powders. They advertised at 4.4 microns, what you get on the bottle or the website. But really, you can see that they consist of much finer subparticle. Here's the iron oxide that we use, and here's the nickel oxide. And most probably those metallic powders were done by reduction, by the manufacturer of much finer nickel oxide, which is precipitated from suspensions, and as a result, are much finer. So it does make sense, right? That this is going to reduce much faster and sinter much faster than those relatively large boulders, which are still, 2 to 3 micron in diameter. Higher magnifications, where we see that this nickel oxide is really sub-microns, so really nanometric, and so is the iron oxide powder. Okay, so as a result, the porosity within the struts, those are cross sections, we see that for iron oxide, because it's very fine, it really sinters very quickly, and so is the case for nickel oxide. Whereas for iron and nickel, we end up with residual porosity that may be in the 4 to 8% region. And we do some passive testing to demonstrate that, yeah, those are fully metallic, they're ductile, so here's a stress strain curve. We see relatively low yield stress. That's because we have pure metals here that are not very strong. A strain hardening, if you want, which corresponds to the more or less uniform plastic deformation of those micro-lattices, and then a densification region where now multiple layers are starting to touch with each other, and it's what we call the densification range. That is well beyond, of course, the range you'd be using it, but the area under the curve here represents the energy that is being absorbed. So for energy absorption applications, this might be also useful. And it's dependent on the relative density, which is anywhere between, around 40% relative density. Here, this is the macro porosity between the struts and also the inner porosity when present within the struts. And so you see very uniform, and so no instability, no shearing, no fracturing, no spalling that you see in other types of materials that are more brittle. So we wanted now to do some in situ X-ray diffraction during the hydrogen reduction. Why? Because we don't want to just look at before and after. We like to see what happens during the reduction itself. And X-rays will allow us to identify which phase are present. This was done at PSI in Switzerland, but we also did work at Argonne, of course, next door for us. And so the principle is relatively easy. You put your ink extruded fiber, so it has polymer and powders and oxide, and then you flush it with argon with 5% hydrogen. The hydrogen is sufficient to get you the reduction. You heat it with a hot blower to whatever temperature. You have, of course, a thermocouple, and then you have an X-ray beam that diffracts and will give us the identity of the phases as well as the volume fraction via the intensity of those diffraction peaks. So here's a diffractogram. We're looking at the diffraction spectrum here over 26 to 36 degrees, and this is as a function of temperature. So starting at room temperature all the way to 1000 degrees C, and so the temperature in red here is simply increasing. This is really simple. This is nickel oxide that goes into nickel. So you see 2 diffraction peaks for nickel oxide, and then you see the onset of nickel showing up at temperatures of about 500 degrees C, and kind of we see that there's a nickel starts to form over 400 degrees centigrade, while still nickel oxide being present, and it's only 200 degrees later that all the oxide has been consumed, forming those very fine particles. And as the grain coarsens, we see that this very broad diffraction peak, which is visible through that kind of fuzzy diffraction, becomes finer and finer, indicating that we have much larger grains as compared to the sub-micron grains that we had before. And so that's relatively straightforward. We go from nickel oxide to nickel with some overlap between the reaction. Now, if we add iron oxide to nickel oxide, so that's got kind of a prototypical steel. Here's what we have. We, of course, have the nickel oxide, so the same story I told you already. We have the iron oxide Fe2O3, and then we start a cascade of transformation from Fe2O3 to Fe3O4 to FeO, and eventually to alpha iron. So iron oxide has those multiple suboxides. And so we see clearly as a function of temperature that we go through what the phase diagram would in fact predict. So really the story would be that first the nickel oxide is reducing, the iron oxide is kind of slightly behind. It then transformed to a mixture of iron plus those suboxides. Meanwhile, the nickel is almost finished. And then the alpha BCC phase transforms into gamma, which is our final FCC iron nickel alloy that is shown here schematically. So that's kind of interesting because the interdiffusion, as well as the is happening, the final alloy happening together with this step reduction between the different oxides. And now we make it a little bit more complicated. We have molybdenum oxide, which also can be reduced. And now we see new peaks for moly trioxide, moly dioxide, and eventually we don't see even moly, it goes directly into the iron nickel. So we're really going from oxide to BCC iron again to FCC gamma. This is now almost steel at this point. So we can print from individual oxide particles and end up with a co-reduction step associated with interdiffusion, end up with a fully alloyed structure. So let's have a look at the metallographic situation. So at the end, I should maybe go back. At the end of our pre-sintering stage, so here we burn out at about 300 BC. Then we are reducing from the oxide to the metal, but there's also pre-sintering happening. And if we interrupt at this point and cross-section and look at the material, we see that iron here, iron nickel, and iron nickel moly all show different levels of pre-sintering. We have not yet gone to the really high temperature to finish them off, but there is a significant sintering upon this co-reduction and homogenization of the material into sub-micron metal particles that are still independent with and not yet fully sintered. And the black is the open structure. And so we go from about 19% porosity to about 28% porosity. You see also other phases here, which are due to the presence of molybdenum. All right, so if we now go from the pre-sintering to the maximum temperature of either 900, 1,000 degree or 1,100 degrees C, which is our final sintering, and then we hold. We hold for about an hour. We see the density jumps from about 80%, what we just saw a minute ago, to about 98 to 99% sintering. And if we zoom in here, we see something a bit unexpected. We see that as we go from 900 to 1,000, actually the sintering is less good. Increased temperature, and yet sintering is not as good, which is unexpected. Normally, increasing temperature means faster diffusion and therefore faster sintering. Only when we go to about 1,100 degrees C do we get an improvement. And we're kind of scratching our heads, but the reason for this is the phase transformation by. This is the diffusion coefficient as a function of 1 over T, so an Arrhenius plot, and normally it's just a straight line. But we have a phase transformation. We go from BCC iron at low temperature, which is kind of going up like this. This is 1 over T. There's a phase transformation to BCC to FCC. BCC is not close packed, so it's rapid diffusion. FCC is close packed. So in fact, the diffusion coefficient D drops as you go from 800 to 900, and only when you're back to 1,100 degrees C do you retrieve your equivalent diffusion coefficient, which explains why we're losing sintering efficiency as we increase temperature from one phase to the other. So that makes sense, and once we understand this, you may as well sinter at relatively low temperatures while taking full benefit of the open, fast diffusing BCC structure. Now, again, looking at density as a function of temperature, we see that the iron, with that caveat from BCC to FCC, really sinters relatively quickly to about 95%. And as we alloy, it becomes more and more difficult to sinter. And that's because also we have slower diffusing, especially the molybdenum is slower diffusion. And so we need to kind of look at the microstructure. This is relatively unsintered, as shown here. And we see that as we go to a higher temperature, the size effect becomes really important. So the mixed oxide reduced, shown here, is much, much finer than the mixed metal, for which we have much larger particles. So this is really the effect of having much finer particles that gives you almost 100%, because we create them from scratch, so to speak, from oxide. Whereas if you start from pre-alloyed powders, or even just pre-fabricated powders, we are plateauing at about 80%. So this is going to be pretty weak compared to that. So that size effect is shown here. And as we increase at 11 degrees C the time, we see a very good sintering here. And this kind of steady state amount of porosity. And it's very, very hard to sinter essentially pores that are 10 micron in diameter. It would take a really long time, really high temperature. And so we never reached that point, even though we are at 1100 degrees C for about an hour. It's getting a little better, but it's still very open. You'd have to do much higher temperatures to get rid of this. So this is the oxide precursor. This is the metallic precursor. We see a big difference in that particular case. The other thing we can do once we have high intensity tomography, this is not done at Argonne, is to do high intensity X-rays. We can do tomography. So we can do a full reconstruction of the material. We don't have the resolution, or we'll barely have the resolution to see what's inside. So the first thing we're going to do is kind of reconstruct that printed structure. So it's about 150 micron in diameter, maybe a millimeter in length. And so this is the surface rendering of that material. So this is colored red to express the fact that we have an oxide. I want you to also focus, there's a little defect here just from printing. And as we reduce it, there's this huge shrinkage discussed already, but you see all the details here are maintained. And as you now sinter to longer and longer times, all the way to about this lag, to about 1 hour, most of the sintering happen after only a few seconds at high temperature. So this is now this alloy using mixed oxide, sintering very quickly at 1100 degrees C. And really, technically, the reason why we're waiting here is to make sure that we have full interdiffusion between the various elements. And you see that the dimensional changes, of course, happen right away. That's the pre-sintering. And then as you pull, let me just show you previously, both the axial and the radial shrinkage are exactly similar, exactly the same. In fact. That's very important. It means that this is a homogeneous shrinkage, which is why we don't warp the material. Everything now is very, very homogeneous and uniform in all directions. So that 40% linear shrinkage, which is about 70% by volume, is uniform. And as I said, having an axial plus radial shrinkage of the uniform means that we don't warp. Warp, for instance, if the axial shrinkage was more than the radial one. And so that explains why we get this extremely high fidelity in the shape while shrinking dramatically. And as shown here, as we go from oxide to metal, this is shiny, so it should be it's not white, it's really a reflection showing the metallic structure in the iron oxide. Meanwhile, we do the same evolution using mixed metal powders, which, if you remember, don't sinter very well. We only get a pretty incomplete sintering of the material because, again, the particles are much larger. And so that's shown on the outside. And so if we now show the two together, we see the oxide-derived material shrinks right away and gets full density, whereas the metal-derived one end up with this internal porosity and therefore much less shrinkage. So it stays really in an intermediate or partially sintered situation. Now, the tomography allows us also to see what's inside. So those are in situ reduction tomographic movies showing the shrinkage of a nickel oxide cross-section under hydrogen. And the colors represent simply densities, so from low density within oxide to high density metal. And you can literally see individual particles that are turning from oxide to metal, and then also sintering, we see the elimination of the empty space And this is, of course, accelerated. You see the time here, because we need to get full 3D reconstruction. This is just one cross-section. So for particles that are relatively coarse, we may not see individual particles, but we will see islands, regions that are denser or less dense. And this combined with the overall shape, right? And the envelope shape gives us information on the kinetics of reduction in that particular case. Okay, so now we'd like to go to so-called high entropy alloys, so or multi-principal alloys, where we have at least 4 elements that are all at the same amount, equiatomic, as we call them. So this would be a cobalt, chromium, iron, nickel, each of those elements being 25%. And we've done, already iron, nickel, and a little bit of cobalt. So what about chromium would be the next one. So so we do a mixture again of cobalt oxide, chromium oxide, iron oxide, nickel oxide. We extrude 3D print, as shown before, is the blended oxide lattice. And after co-reduction and sintering, we have, again, a very nicely conserved geometry, but highly shrunk microstructure or architecture of the material. So that works. And you say, well, okay, so what's the big deal? The really interesting thing is that chromium oxide, if you look at the stability of chromium oxide, should not be reduced with hydrogen. It is more stable. It's sufficiently stable that pure hydrogen will not reduce chromium oxide. So what we achieve here is a reduction of chromium oxide in the presence of already reduced cobalt, iron, and nickel. And I'll explain in a second why this is happening, but let's look at, we start with those extremely fine powders or powder agglomerates where we have all 4 elements. And at the end, we have now a nicely fully sintered material. You see some twins here, you see grain boundaries. This is exactly the kind of structure you'd get if you were casting that very alloy, which is multi-principal element, as I said before. So now we can do that in situ diffraction on the material. This was done at PSI again. So this is what it looks like. So let's just go one by one. The temperature is increasing here. So time, if you want, is increasing here. So at first we have the 4 oxides. And you see that it's slightly canted here. So this is the thermal expansion of the materials, which changes the lattice spacing. Then we have rapid reduction and formation of iron, nickel, and cobalt. So the oxides disappear. You see they're gone here. The iron oxide is gone. And instead we have BCC iron, FCC nickel, and FCC cobalt. So those are individual particles that are reduced. And the next step, I can get this to work, is interdiffusion of iron with nickel and cobalt with iron. So we see now this FCC iron nickel intermediate alloy, as well as a BCC cobalt iron. So they are, of course, different crystal structures. So we end up with different diffraction peaks. And then finally, you see that the chromium oxide had done nothing. It was simply sitting there, because after all, it's supposed to be stable. But then it disappears at the highest temperature here, and you get a drift of that diffraction peak, indicating that we're alloying with chromium. And in fact, the cross-section that I showed you, if you do EDS, you see that it is really fully homogeneous. So at the very last moment, the chromium oxide disappears, and we end up with a single FCC cobalt, chromium, iron, nickel, entropy, or multi-principal alloy. So if we look now as a function of temperature at the intensity of those diffraction peaks, that is going to give you how much material is. So we start with all the oxides with their original intensity. It doesn't matter what the value is. What is important is that cobalt oxide disappears first, then the nickel oxide, then the iron oxide. All of this at roughly low temperatures, right? Between 300 and 400 degrees C. They're all reduced, they interdiffuse, and they're in contact with the chromium oxide here. So here's our kind of pre-reduced cobalt, iron, nickel. And only at the highest temperature, the chromium disappears. And the reason for this is that it's on the verge of being reduced, and it reduces a little bit of the hydrogen, and then the product, which is chromium, dissolves in the neighboring cobalt, iron, nickel. So you're driving the reaction from chromium oxide to chromium because you're extracting the product. This is 18th century Le Chatelier, which is how to move how to shift a chemical reaction by removing products, and therefore continuously pushing the reaction, which is now the chromium oxide going to chromium. And at the end of the day, you end up with a full reduction of chromium oxide, unless, of course, as the sintering also takes place, unless your chromium oxide becomes encapsulated by a sintering matrix, of course, of the iron, nickel, cobalt. So we have kind of a competition between this hydrogen reducing the chromium oxide, and as long as it's exposed to the surrounding atmosphere of hydrogen, it can reduce, and then the sintering and shrinkage that happens that may encapsulate the chromium oxide before it's reduced. And we can see this really in those interrupted structures. So here is the low temperature where you have freshly reduced iron, nickel, and cobalt, and you see chromium oxide particles that in fact inhibit the sintering. So they are simply preventing the iron, nickel, cobalt from sintering together, which is good. We need porosity to get access for the hydrogen to come in and reduce and the steam to come out. In some cases, we start encapsulating. You see the dark chromium oxide particles. In some cases, at high temperature, are encapsulated. So that's game over for those. I mean, they're not going to be reduced anymore. Meanwhile, you have larger ones that are still exposed to hydrogen and will reduce. And so at the end of the day, in that particular case, we see a nearly fully reduced structure with a few tiny little inclusions. So they're actually oxides of calcium, magnesium, and silicon. This is impurities that existed in the original pure iron powder, iron oxide powder, and nickel oxide powders. You buy them at 99.5%, but there's always a little bit of impurities, and those are completely stable. They will not reduce under hydrogen. You also see how this slumped structure, right? This was a single extruded strut, but because it had relatively high, low viscosity, it kind of slumped. And so this is why you get kind of this cube beam structure. All right, so we end up in that particular case for this equiatomic alloy with nearly fully dense materials. This is porosity on log scale, so this is 0.1% here. We also get some grain growth, higher temperature, from submicron to tens of microns. And those are relatively coarse grain structures compared to the diameter of the filament. So we have what we call an oligocrystalline material, where the number of grains through the cross-section is less than 10, typically, which is going to give us some variation in mechanical behavior, depending on which grains are oriented to which angle. And so we did mechanical testing on single filaments, so the extruded filaments. And so here's the room temperature properties, yield stress, a lot of strain hardening, 30% engineering strain in tension. So this is clearly a ductile material, and it's very similar to the properties that are reported for cast high entropy alloy of that composition. And where those materials shine is in the so-called cryogenic temperatures, with 130 K here. And we see, of course, a high yield stress as expected, but still a huge amount of ductility at cryogenic temperatures. Unlike, say, BCC material that become extremely brittle once you're cryogenic. So this is a good combination of strength and ductility at cryogenic temperatures. Now, this is for the filament. Now, once we make a lattice, shown here, we of course get much lower strength, but also excellent, and this is in compression, I should say, so it's maybe the ductility is maybe less impressive than in tension, but you see that the effect of temperature on the strain hardening, as well as the yield stress, and of course, still very, very good ductility in the material, and so energy absorption capability at cryogenic temperatures. So let me see. So depending on how much time I have, do I have still a bit more time? I think probably 5 minutes. So 10 minutes, fantastic. So far we've really talked about iron, cobalt, nickel, and chromium, right? But what about, and moly we did as well, but what about some other oxides, in particular tungsten? So tungsten is really interesting, right? This is a high smelting element, very hard to sinter if you start from powders. But nature is kind. Tungsten oxide is relatively unstable, so you can reduce it with hydrogen, just like we've done for the others, end up with tungsten steam again, which means that we can create submicron tungsten particles that hopefully will sinter fast. just like I showed for the other side. So we really wanted to demonstrate tungsten, and it works. So I'm going to go a bit faster here. Right? We have tungsten oxide. We add a small amount, about 0.5% of nickel oxide. The reason being that tungsten with nickel sinters much faster than pure tungsten. That's because it creates a transient liquid phase. I'll show you in a second. So here is our printed structure, and here's our sintered and reduced and sintered structure. And you clearly see the beautiful struts. You see a cross section here, and you clearly see segregation of the liquid phase that accelerated dramatically the sintering. This is now fully sintered tungsten at a temperature which in that case is about 1300 degrees C, which is really low temperature for tungsten. I mean, tungsten normally with that nickel would need easily 2000 plus for sintering. This was known, right? The nickel effect was known, but on particles of pre-reduced tungsten, not so much on nascent tungsten from reduction of tungsten oxide. So we are pretty pleased with it. So here we are. We printed 200 micron nozzles. It shrinks, and so the diameter now is below 100 micron. Probably impossible to do this with laser melting or e-beam melting without cracking terribly and all kinds of terrible surface asperities. We see very smooth surfaces here. This is 1 hour at 1400 degrees C, and of course that dramatic shrinkage that I discussed. So that's of course the Achilles heel of the no. Here we are. So now we played a bit with the sintering time. This is a fracture surface. This is a cross-section surface. I want you to look at the size of the grains, but you can see both in cross-sections and in the fracture fractography. So this was 1 hour at 1400 degrees C. Maybe I'll just do it this way. We see now for 4 hours, you see the grains have grown as expected, but it's still pretty fine grains. By the way, this is important, right? Fine grain tungsten has ductility that coarse grain tungsten does not have. And if you go even shorter time, from 1 hour to a quarter of an hour, we even have much finer grains, albeit we start seeing some porosity. So we have that control over grain size and therefore the intrinsic ductility of the tungsten. And now if you change the sintering temperature, this is again the baseline 1 hour at 1100 degrees C, fracture surface or cut surfaces, we see very fine grain. And if we go now to 1200 degrees C, let me go back. This is 1100. Again, look at the grain size here. You get, of course, coarser grains as you go at 1200 degrees C, very smooth surfaces. And again, if you watch, as I go to 1300 degrees C, we see even coarser grains. This is now becoming oligocrystalline. We have maybe 10 grains in the cross-section, or maybe 5 or 6, as shown in the cross-section here. So that will now become somewhat anisotropic in its properties. And we don't have to keep just those empty lattice structures. We can also create composites. So this is a typical example where you now infiltrate the tungsten, which is brighter here, with copper. So liquid copper does not dissolve tungsten. It's completely compatible. It wets, and simply by dipping it in copper, you can now make a copper tungsten composite with this internal, very regular structure. And we do this mostly because we can achieve in the composite a coefficient of thermal expansion that is between that of copper and tungsten. This is the extension as a function of temperature. We see copper has a thermal expansion that is much higher than tungsten, reflecting the differences in melting points. And of course, the copper tungsten composite now has a thermal expansion that's in between those of copper and tungsten. It's really interesting because in many cases, you would like to match the thermal expansion of material, especially in cooling situations, or if there's big swings of temperature, otherwise you start delaminating. And both copper and tungsten have very good thermal conductivity, so you end up with excellent thermal conductivity. In fact, commercially, this is what you get, a tungsten 25% copper composite, but where the folks at the plant just infiltrate tungsten particles with copper, which is very different from this. You can imagine that this is a much better thermal conductor because you have channels of pure copper. We did not measure it, but we expect this to be much better. Meanwhile, because it's a 3D lattice, it has a relatively isotropic thermal expansion. Not quite as good as this situation here, but definitely quite interesting. Now, with the few minutes I have, I just want to show you, again, with tungsten, which is the most difficult material to work with, that we can go well beyond just those simple lattices. We can create so-called gyrate structures, which if you see are 3D structures, load-bearing, but without stress concentration at contact points between lattice struts. Also, even though it's not quite easy to see, this gyrate structure separates two volumes, which are not communicating with each other. So it's can be used for a heat exchanger system that is very homogeneous. So that's just the topology of those. So we print with tungsten oxide, which is this kind of greenish shape. It has a support around it. We then sinter, and then we machine the support and end up with those gyrate structures. And relatively going a bit fast, we see that the porosity can go down to near 0%. So we get fully sintered tungsten structures at 1400 degrees C with a little bit of nickel, as we had before. If you don't do things right, if you don't mill correctly, you end up with a lot of residual porosity. And you see that the stress strain curves here in compression, of course, we see that at room temperature in blue, the gyrate is relatively brittle. Sense we are below the ductile to brittle transition temperature of tungsten, so the material is as brittle as a ceramic. So it kind of goes to about 20, 30 MPa and then fractures miserably. At higher temperature above the DBTT, we now have a much higher strength and then a rather gracious fracture without complete shattering. And so the energy absorbed is much larger in that particular case. And I think for the interest of time, because we did this on multiple structures, so as a function of relative density, we can measure the compressive strength. Those are simple models for the relationship between those two things. And I think in the interest of time, I would just jump now to the conclusion. So just summary, we use inks with oxide powder suspensions by combining powders, elastomers, and solvents. 3D printed into complex architectures, from lattices to those more complex structures I showed you now. There is reduction and sintering happening, leading to large volume changes without warping or cracking. This is shown here. This can be extended to metallic or even non-oxide powders. I didn't show this, but we can also print with hydride, for instance, and then decompose the hydride. That's a very good option for titanium. Print titanium hydride, decompose, and form titanium that sinters. The stress can be dense, like in the tungsten, or porous, like in that nickel example, if we want to get additional porosity. And then we did X-ray tomography to get the outside shape as a function of temperature, and X-ray diffraction, which tells us the sequence of phases that happens during that cascading reduction from oxide to metal and into diffusion to form alloys. And we gave examples for iron, nickel, cobalt, copper, tungsten, as well as a high entropy alloy here. And I have ongoing work where we're pushing those concepts to even more complex alloys. Thank you very much, and I'm happy to take any questions you may have.
So just a few minutes for any questions.
Yes.
Fantastic talks. So this kind of method remind me right now some community talk about how to produce steel in a green ways, like use hydrogen to reduce. Because in that community, the major problem is this slow reduction kinetics for hydrogen reduction for iron oxide. So I wonder, do we have similar problem, like this kind of reduction could take too long time?
Very timely question. So I literally have a new NSF project where we're using those concepts to do green steel, right? So reducing iron oxide with hydrogen that's been produced from electricity that is green, at which point the carbon footprint is zero for the reduction part. And yes, so very similar issues. So we do not want to clog or we want to keep the particles, so the ore particles. This is not ore, right, coming out of the ground. And the ore particles are often agglomerates of finer particles. In some cases, they are dense. And so you want to keep them open so the reduction can take place as fast as possible without this encapsulation I described, which one is much harder to really have essentially the oxygen ion going through a layer of iron out and reacting. So very much the same issues. And in fact, we're thinking, well, it's part of the proposal, we haven't done it yet, of co-reducing, just like I showed for the high entropy alloy. So we put, say, iron, nickel, chromium, and we can create in one go stainless steel without ever melting at 0 carbon footprint. So that's upcoming. I'm happy to provide more information in about a year when we have done this. But thank you. That's a very, very truly excellent question.
Again, thank you for this great talk. I really enjoyed it. Since you're doing reduction in the hydrogen atmosphere, are you also trapping some hydrogen in the metal?
That's a really good question again. So you're absolutely right. There's this possibility of doing this. So at the end of the reduction, we switch back to argon, and then we degas. You're absolutely correct. It would be not good to have some leftover hydrogen. Yes, and I didn't mention it. Sorry. One more question. Okay.
So I'm wondering what limits the resolution of the printing for maybe the thickness of the thrust? Is it the rheology of the polymer or the strength?
It's very practical. It's really the clogging of your extrusion syringe. So we can get them all the way down to 50 micron, right? Especially for polymers or for liquids, it's relatively easy to extrude 50 micron. By the time we have particles, it's more viscous, the pressure increases, and often we have clogging if we have agglomeration of particles. So if your particles are sub-micron, like we're using, that's number one, and if more importantly, they don't coalesce into agglomerates that may be larger, we are able to extrude down to 50 micron, which after sintering, now that's the shrinkage that helps us, right? It goes down to 25 micron. So it goes from 50 as extruded to maybe 25. Much below that is probably not possible. And there are many papers that go to much finer structure. Those are kind of the 2-photon parameterization. Those are minuscule volumes, but much finer structure. So it's kind of filling a gap, if you want, between those very small volumes, very fine microstructure, and the more macroscopic extrusion that you can see that may create, tens of centimeters diameter. The kind of stuff that the catalytic converters are, kind of honeycomb structures. Those are extruded ceramics, yay big meters. So we're somewhere in between. Thank you for your question.
Okay, let's take our speaker once again. Okay.